Perfect. I think we are yes. I think we can start. Yeah. So welcome to the tutorial about 3D modeling for indoor panoramic scenes, and I will give the floor to the organizer of the event, Dr. Enrico Gobetti, that he will provide an introduction for this tutorial. So enjoy. Enrico, the floor is yours.
Can you hear me? Can you hear me? Okay, that's fine. I'm starting to share the screen with the slides. Okay. This should be this one. Okay.
Okay, you can go.
Okay, I'm just going to admit some people in the room. Okay. Okay, so welcome to the tutorial on on automatic 3D modeling of indoor structure from panoramic images. Today we are going to try to make things work despite the fact that we had quite a few problems with settings. Before starting, let me briefly introduce the organizers and speakers of this tutorial. The first person listed here is Giovanni Pintore, who is a senior researcher and engineer in my group, the Visual and Data Intensive Computing Research Group at the CRS4 Research Center in Italy. One of his major research focuses is in indoor reconstruction, and more specifically in panoramic images, which is the topic of today's tutorial. He has an extensive publication record on those topics and has already given tutorials related to these problems, both at SIGGRAPH, Eurographics, and 3DV. Marco Agus, who is locally present, is an assistant professor at the Hamad bin Khalifa University in Qatar, where he works the boundary of computer vision, computer graphics, and visualization. Before joining the current university, he held a research position at CRS4 and at KAUST in Saudi Arabia. In the field of indoor reconstruction, he is more interested in the visual representation part and in the exploration. On the related topics, mostly related also on using mobile devices, he also gave already tutorials at SIGGRAPH and Eurographics. Finally, myself, I'm Enrico Gobetti. I'm the research director of the Visual and Data Intensive Computing Research Group at CRS4 in Italy, where both Marco and Gianni have worked or still work there. My activity spans many areas of visual computing, and indoor reconstruction is one of them, and I really enjoy working with Gianni and Marco on the subject we discussed today. There are more details on the background and that we have and on our works on the project website. And the people that attend in presence can also chat with Marco, who is in Vancouver, while me and Gianni were forced to present remotely due to some problems we had. Okay. Now, let's look a bit at the schedule that we have today. We have divided the tutorial into two main sections, separating them by a short break. Wait a minute, because I'm the host and I need to admit the people in the room. Okay. After the short opening that I'm giving, I will have a session that is going to introduce the topic of indoor capture and modeling. And my goal will be just to provide some context to the next talks. After that, Gianni will focus on room modeling, focusing mostly on the methods to finding bounding surfaces of a single room or environment by intelligently exploiting a series of priors that we will discuss. A major portion of the talk will be on recent deep learning solutions that are capable to extract information from a single shot. We'll then have a short break. The people in Vancouver can enjoy the cafeteria, while here we'll just have a short pause. And after the break, Gianni will continue moving on the topic of integrated model computation. We will focus mostly on multi-view solutions and the reconstruction of multiple rooms environments. This will end the pure reconstruction part, and Marco will then move beyond the problem of reconstructing geometry and structure from data, and will focus on issues that are more related to reconstructing and editing appearance and style, so moving to the visual part of the problems. And there will be some discussion also on how to explore the panoramic models. We'll then conclude the tutorial with a short wrap-up and Q&A session that will be even local or online. Now, in addition to what we will present today, I want to point out that we have some supporting material. First of all, we have a project website, which is also listed on the main CVPR tutorial webpage. Right now is pretty terse, but and contains just the core description, but we will be updating it in the coming weeks with a copy of the slides that allow recording. Okay. With a copy of the slides, and we will also include some text and some bibliographical notes. We also refer you to some related materials based on our previous publication that I think will be useful, and they are available on digital libraries. The first is a comprehensive survey that we published together with colleagues from Zurich and CNR in Italy on indoor construction from several data sources. While it was published in 2020, it still contains a comprehensive overview of the field and a set of classic references. It doesn't cover just panoramic imaging, but panoramic imaging is one of the things that are discussed in there. We also delivered a tutorial at several conferences, and for SIGGRAPH 2020, we have supporting material that is available on the ACM digital library that can be combined with this, what we will provide here and what is presented in the state-of-the-art review to give a complete overview of the topic. Having finished this introduction to the talks, let's introduce the topic itself. So the topic that we selected for this tutorial is automatic 3D modeling of indoor structure from panoramic imaging. So there are a lot of things that needs to be put in context. Automatic 3D reconstruction from panoramic images is in itself a major subfield of what is indoor reconstruction. And indoor reconstruction is now recognized as one of the most rapidly developing areas of 3D reconstruction or 3D surface reconstruction in general. This 3D reconstruction field, there are several device types that they sample a collection of measures of the environment. This collection can be noisy, sparse, whatever, but they provide measurements of some property of the environment. It could be color, it could be depth or something. And from those data, you need to extract a clean and application-dependent 3D model that we need to infer with some constraints that are given by the application. As we will see, indoor environments, as well as the target applications where the data from indoor capture is used, have very peculiar features that make the problem different than general 3D reconstruction, and also very challenging. In this tutorial, we want to provide a view of the research carried out in this area with a particular focus on panoramic images. Now, let's define this focus more precisely. First of all, we don't want to specifically discuss the acquisition part, but we concentrate on the reconstruction pipeline from the acquired sample. So we don't discuss acquisition protocols, acquisition devices, and so on, but we focus on the rest of the pipeline from when we have the data, that for us is panoramic images, to when we exploit it. Second, we mostly target 3D reconstruction, as opposed to solutions that only strive to generate 2D floor plans, which are a major portion of the application. What we want is to not only reconstruct the floor plan in 2D, but also have some version of the 3D environment. In terms of pipelines, moreover, we do not target the interactive acquisition or the manual modeling, but rather the pipelines that process automatically the data and reconstruct the models from the acquired samples. This is important because several pipelines that have been proposed require the user to operate the device in some particular guided way to obtain the model. What we want is to have the data from the device and then process it in the most automatic way as possible. Moreover, as opposed to plain surface reconstruction, the goal is most of the time not to replicate the dense surface and appearance details, but to discover architectural elements, indoor objects, and to organize them in some consistent structure, which is visual and geometric, that captures some relation. This requires some sort of understanding of the scene. For instance, to separate architectural elements such as walls, floors, ceilings from the clutter, which is often referred to as the furniture, for example. And finally, this tutorial, among the many capture modalities, has chosen to focus on panoramic images. We have a reconstruction that work on many images from regular cameras, from laser scans, from RGBD, and so on. And our selection was to focus on panoramic images. This means that we have a 360-degree image that samples the entire environment around the viewed location. Why we want to focus on this? Because panoramas, in fact, are at the center of much research and application work. Now you will see many papers, even in CVPR this year and at other conferences that focus explicitly on panoramas. And they are becoming one of the prominent acquisition modes for indoor reconstruction and exploration. And there are several reasons for this popularity. First, there are many acquisition solutions available, from commodity and professional devices like 360 cameras, which capture panoramas in single shots. You have professional ones and also very low-cost ones that are available, but there are also several software solutions that stitch multiple images into panoramas. Second, acquisition is generally easy and fast. If you take a 360 camera, taking a single shot per room allows you to have indoor mapping in a matter of seconds. Third, the acquired images provide plenty of information from the reconstruction process, which makes them immediately different than a regular image. In fact, there is some global context that derives from the fact that you have your 360-degree view that facilitates the analysis. There is no clipping of objects, of areas, of boundaries, and there is vast possibility to exploit scene irregularities, symmetries, and so on that can allow you to deal with the reconstruction. And finally, if we discuss the movement from reconstruction to visualization, 360 images are different from the regular ones because they are not consumed at once. The exploration of even a single image is dynamic and immersive. A typical way of doing it is in VR to rotate the head to view a panorama. And this makes them, even a static image, something which is dynamic and fundamentally different than standard 2D counterparts. For this reason, for example, they are one of the main media used in current VR applications. So, okay, for panoramic images, we have seen why they are so important. But now the second obvious question is at this point, why do we need specialized techniques for interior scenes? Why don't we talk about just panoramas in general? Well, it turns out that in many specific fields, there is a strong need for structured indoor models, which are a high-level representation that abstract the low-level measurement into the main scene elements and their relations. And these representations have to meet some specific needs. For instance, if you talk about architecture, engineering, and construction, there is often the need to generate and update building information models, which are largely focused on architectural structure of the environment. So this means that, for example, from an image, you are interested only in the parts that reconstruct walls, floors, ceilings, and so on, and you want to remove the furniture. On the other hand, there are applications like, for example, emergency management, indoor navigation, and so on, that need to have such a representation, for example, to recognize where you have the doors and so on, but they also need to have information on the clutter to, for example, define the paths. All these needs are specific and they are not guaranteed by standard surface reconstruction. On top of this, specialized solutions are also needed to solve ambiguities that are inherent in reconstruction from acquired samples, because interior environments, as we will see, are often cluttered and have many unreachable areas. This means that there are a lot of parts that are unseen, but you want still to reconstruct. Moreover, they contain a vast amount of textureless surfaces, as well as reflective, transparent one, which give rise to a number of specific artifacts that I will discuss shortly. Okay, so generally speaking, artifacts that one can expect to find are the same that one may expect to see in general surface reconstruction. So we're talking about noise, outliers, uneven sampling density, misalignments, and missing data. However, in the case of indoor environments, these artifacts take some specific forms and are more or less evident depending on the specific environment or acquisition device. And we see here what happens for panoramic images, for example. If you talk about noise and outliers, all the acquisition technologies generally exhibit some degree of measurement noise and have problems with transparent and highly reflective surfaces, because these generate either noise somewhere or ghosting artifacts. So measures that indicate some geometry that actually does not exist, for example, in the case of mirrors. These surfaces are abundant in 3D environments that are indoors, and so must be dealt with. Sampling density is also very uneven. You cannot count on regular sampling densities. For example, if you use rectangular images, which is one of the main projections for panoramic images, the sampling ray density decreases with the vertical distance from the center. Moreover, geometric surfaces that are facing the viewer, for example, the front wall, are sampled more densely than those that are tangent to the view rays. And also, if you have a lot of textureless regions, for example, typical walls that are painted in some non-reflective surface and so on, you cannot extract some stable features everywhere, because all the image looks the same. This means that you have a lower density of 3D points if you want to use some multi-view approaches. And also, there are, even if you use a single view, there are less features in a single images that you can use if you want to do some geometric reasoning. Problem with misalignment can also occur in multi-view acquisition, because you can have errors in the localization of individual frames. This is a relatively standard problems for multi-view, but as we mentioned before, since you have not a lot of feature points that are detected in textureless areas, it is often harder to align multiple views. On the other hand, high amounts of missing data are probably the most distinctive trait of indoor scenes, because of the clutter and the narrow spaces where you walk. This makes it difficult to capture inaccessible parts of the scenes, and originates many shadow areas, included areas that are caused by objects or walls, including the line of sight of the sensing device to the structure of elements. You have some areas that you want to reconstruct, but you have no measure for it. So you have to use some extra information to do the reconstruction. And the extra information that you use is based on the fact that you know that you are reconstructing an indoor environment and not a generic model. So in order to reconstruct the noisy, partial, imperfect data, you use priors. This means that the images are interpreted under the assumption that the photographed model has some known characteristic, and by imposing such priors, you reduce the solution space. This makes the reconstruction easier and the resulting model more plausible. Obviously, if the scene matches a prior, otherwise everything fails. But if you have a scene that matches an imposed prior, this information allows you to reconstruct models even with very few measurements. In indoor reconstruction, we employ a series of geometric priors that are also present in typical surface reconstruction methods, for example, smoothness of surfaces, continuity, and so on. But most importantly, there are very specific architectural priors that derive from the way interior environments are constructing. So these are architectural for that reason. I just mention here that there are not a single way to interpret an architectural space, but in the course of the research in many years, several specific priors have been proposed to handle some specific subset of the environment. I will present them here, at least the most common used, in increasing order of complexity. The most restrictive one is the floor wall prior, which assumes that the environment is composed of a single flat floor, so a single flat surface, and a straight vertical walls. So we basically ignore the ceilings. The cuboid prior assumes that the room has a cube-like shape, so it's bounded by 6 rectangles placed at right angles. So the task of reconstruction is to find these 6 rectangles that form the cube. Okay. According to the indoor world model, the environment must have an horizontal floor and ceiling and vertical walls, which all meet at right angles. This is a slightly more restrictive version of what is known as Manhattan World prior, which is probably the most widely used prior, which allows floors and ceiling to be at different elevations. The Atlanta World priors, or also called sometimes augmented Manhattan World, lifts the restriction that walls must meet at right angles. They are still vertical, but you have more freedom in placing the walls. If you want to allow the floors and ceiling to be sloping while keeping the verticality of the walls, you obtain what is often called vertical walls plier. And finally, what is also used in some works is the piecewise planarity, which means that we can also have sloping walls. So in this final case, rooms can be general polyhedra. This assumption is the least restrictive, but at the same time, it requires a full 3D reasoning on the scene. In the ones that have vertical walls, you can have some projection that on the floor provides you some information, while in the general piecewise planarity version, you don't even have that possibility, so you have to work on full 3D. Historically, the priors were exploited in geometry reasoning solutions that combine them with some specific process to extract the models. What do I mean by geometric reasons? For example, classic pipelines, what they did is to extract edges and corners in 2D from the images, lift them to 3D while filtering them according to some Manhattan direction. So saying, if I find a corner and it matches some vertical or horizontal edge and the edge across at right angles, they must be the corner of a wall and so on. So you can reason that way, and you try to connect and match this feature to obtain a consistent 3D model. This has had some important results, but the quality of the reconstruction is heavily dependent on the quality and quantity of detected features. And as we have seen, it's not easy to detect features in 3D environments that have all these texturized surfaces, a lot of occlusions, and so on. So nowadays, more and more solutions exploit instead some data-driven pliers. So the idea that we can extract some common characteristics that help us to do the reconstruction from large sets of examples. And deep learning methods in particular are emerging as an effective way to discover such interrelations from large data. The most common class of methods, however, do not use typically just a single solution, but mix a bit the various approaches. For instance, there can be some pre or post-processing based on some assumption connected with deep learning pipeline and so on. We will see many of the solutions in the following. If we want to do this sort of work, we have to work on data sets that are available. There are many research data sets that have been published in recent years that can be used for general indoor reconstruction or specifically for panoramic images. We do not have the time for an in-depth description here. For additional details, we refer you to our survey article and the tutorial website that we will update in the coming weeks with links to several important data sets. The importance of the data sets is explicitly very, very important, as I say, for deep learning solution. So to wrap up, what we can say is that panoramic imaging, single or multi-view, has important characteristics that have made them very popular and important for indoor reconstruction and exploration. These characteristics include the fact that there is a wide availability of devices, capture is easy, the coverage is complete around the viewer, and the media nature that you obtain makes them dynamic and immersive. Captured information, despite the fact that you have a global context, is never perfect and complete. And the indoor reconstruction is thus to build some application-specific models that allow us to interpret partial, noisy, imperfect images. What is important is that we have to cope with noise, uneven sampling, misalignment, missing data, and so on, in order to build some structured model of the scene. This is possible only, as we will see, by exploiting priors, which include generic surface reconstruction priors, such as surface smoothness, but most importantly, also specific architectural priors and the emerging data-driven priors derived from large data collection. The various techniques that have been developed differ basically in the priors that are used, and that limits their applicability, and also in the way the priors are exploited to build the models. In the remainder of the tutorial, we will analyze the techniques that now form the state of the art. We concentrate first on the methods for single rooms and often use a single view approach, so single image, full reconstruction, to later move to constructing multiple room models and also using multi-view. Finally, we will go beyond structural and geometric reconstruction to also touch visual representation generation and exploration. So now I close my first introduction, and I leave the floor to my colleague Giovanni Pintore, who will start with room modeling.
Well, thank you.
Okay, I stop the sharing.
Well, I will start sharing my desktop, okay, and then here we are. Can you see the slides?
Yes, yes.
It's clear, okay. So, hello everybody. Thank Enrico for the kind introduction. I'm Giovanni Pintore, and I'm going to present this session titled Room Modeling. Despite its simple title, this part describes the major fundamental techniques supporting 3D modeling of full indoor structure. And the modeling of individual indoor spaces, commonly identified with rooms, is the fundamental task in indoor environment reconstruction and modeling. In this case, of panoramic images, the expected input is at least one image for each room or individual spaces of interest, or few images specially referenced. The expected output can be an abstract 3D model of bounding surfaces, as Enrico said, like structured, for example, into walls, floors, ceilings, or a set or pixel-wise and geometric and semantic information. Also useful for defining other types of models, like, for example, for interactive editing or VR navigation. These outputs can eventually be combined across different rooms to model more complex environments, as we'll see, for example, in the next session after the break. A specific property of panoramic images is that reconstruction can be done just from a single image, so that most of the methods in the literature are of this type. Two fundamental tasks are common for room modeling. The first one is trying to estimate the pixel-wise information, and the second one is recovering the 3D indoor layout. For the first task, we reconstruct information that matches with a visible pixel, as for example, typical is depth, normal, semantic estimation, and also in this case, 3D reconstruction is limited to the visible point cloud and its properties. However, the information recovered is assumed to be a dense 2D map. The second task instead is recovering a 3D structured layout, consisting of reconstructing the geometry of the bounding permanent surfaces underlying the scene, as we have seen in the previous section. That involves an abstraction of the 3D model, which is basically approximation. Such representation is often sparse, like, for example, a set of corners or edges. And it should be noted that it's very common in this context to define as 3D layout only the bounding surfaces, even if the 3D layout, of course, is a more general concept, which actually should involve all the scene objects and also other functional parts. In our case, we are interested in the permanent structure of the layout, like in many papers, and the layouts intended as a combination of walls, floor, and ceilings. Okay. The pixel-wise reconstruction is that we have many examples of this. The first one, the most common, is depth estimation. Because of its natural conformation, is input and output are fixed size maps. So the problem clearly naturally fits in depth learning methods. Such methods are usually supervised. That can be also be self-supervised, but less common even for kind of accuracy problems. Almost all methods follow an encoder-decoder scheme, which is valid for multiple targets. In fact, just changing the latest layer size and the activation functions, we can also change the kind of output we have between, for example, depth, segmentation, or normal maps. One of the first papers use a approach depth estimation problem was the FSRM. This work targeted for binaural images, perspective common images. So it's a very now is the most widely used baseline, even for later work as well. Among the various solutions adopted by this approach is should be noted that they use residual blocks and also the reverse Huber loss function for training, which are still commonly used. However, this early solution was not really optimized for indoors. We don't have any priors about indoors here. And neither for spherical images, so suffering their distortion. That is, in this way, simply adapting the baseline leads to poor results for indoor panoramic scenes. Later, many other specific solutions targeted for omnidirectional images were studied, like, for example, OmniDepth. Here, OmniDepth extends the baseline of FSRM using distortion-aware kernels with the intent of mitigate spherical distortion. On the other hand, pano pop-ups exploit the indoor prior based on about the concept of planarity. In both cases, work individually. One works only on the spherical distortion, the other one works on the indoor prior. But the main problem of such approaches is that the performance is limited and because there is a very increasing computational complexity in such approaches. Then later, several approaches arrived and adopt a dual branch architecture with the goal of exploit both the spherical wide context for this, in order to undistort the images. And here in the example, diffuse both branches adopts a conventional encoder-decoder scheme, one for the original equirectangular image and one for its cube map projection. The information exchange between the branches is done at feature level. Several equirectangular to perspective and perspective to equirectangular transform are applied to the features in order to perform a kind of gated fusion. It is also typical in sparse-dense approaches, for example, where, especially in context where all the pixels are not valid or are not in the same reference space. As a counterback, the dual branch has a high computational cost. In the latest improvement, the same authors improve the original pipeline and introduce a self-supervised approach by exploiting a photoconsistencies between three adjacent panoramas with a less computational cost of the original pipeline. The methods seen before adapt generic perspective baselines to spherical images, so trying to reduce the spherical distortion and without considering the inner features of the scene. Instead, a new generation of methods seeks to directly exploit the native encoding of equirectangular images and the indoor scene assumption. One of the first work of this kind is the SliceNet. Such a work starts from the assumption that man-made structures are usually designed according to gravity. So, for example, walls are vertical, and the scene generally varies more along the horizon, in a panoramic image, than the vertical direction. Furthermore, since the indoor scene is represented as a spherical view, image feature can be encoded as an asymmetrical encoding that is contracting image columns, also known as slices. This work only along the vertical direction. And as a result, the image is encoded through a cascade of contractive convolution, which reduce only the vertical dimension, returning a sequence of compressed features along the horizon dimension. So, once features have been flattened in a fixed size sequence of slices, a feature refinement strategy is applied to recover long and short-term spatial relationship between slices. The SliceNet implementation features are refined through the LSTM module that is a kind of transformer ancestor in some ways. Once refined, the compressed feature can be convolved and upsampled since to reach the desired output resolution. More recently, modern techniques such as transformers or nerve-based methods have been applied to this problem. In fact, the main problem in feature compression is the losing of small details. Panoformer tried to address this problem, converting panorama into tangent images, but also adopting a PST strategy and a transformer to keep track of long and short-term spatial relationship. Another recent trend is also using neural radiance field theory to solve orthogonal problems, like in this case, depth estimation. Here in this example, of this last CVPR conference, we show multi-view panoramic approach, which achieve better results in depth estimation from motion. This is still an early approach. Here is just compared with structure from motion. It's not comparable to single panoramic method, supervised single panoramic method trained and tested for large-scale data. But anyway, neural scene representation is used basically to support self-supervised loss. And notably, indoor priors are adopted for the wake initialization. To summarize this part about pixel-wise reconstruction, recovering the pixel-wise information is a fundamental task in image-based indoor reconstruction, because such information goes beyond that and includes other multimodal data essential to build structured models. Furthermore, information recovered from a single image can be integrated with multiple views, and also needed to improve holistic and semantic understanding. However, several open problems remain. For example, current pipelines are limited in resolution and computational scalability, where one of the main problems is the memory needed by the network to work. Sometimes, as we have seen for the double branch architecture, we see that we have a moderately low number of parameters, but we have very increased use, a huge use of video memory. Another aspect is the multi-frame consistency. Very few works address this problem. This is still a limit for an effective integration of dense single-view prediction and structure from motion pipelines, for example. In this case, multiple prediction, for example, from near position, will be not consistent in terms of geometry and lighting. And then, once we have seen the first part about the pixel-wise dense reconstruction, now we go more in the concept of 3D layout and abstraction of 3D layout. This is another fundamental task itself, even considered only from a single image. Layout reconstruction means reconstructing the shape of the so-called rooms. So, possibly by deriving the structured model in its parts. Such rooms can be derived from one or more images and combined with each other and can put together to form a more complex structured model. In the panoramic world, it's very common to reconstruct individual rooms even from a single panoramic image. This is for several reasons that Enrico has already mentioned before. The first one is availability of images, where taking a single spherical image is much easier and more practical, of course. A single panorama, for example, can be obtained just by stitching with a regular smartphone. And also we have a lot of compact spherical cameras that are controllable from with a smartphone and so on. So another problem is also that even having more images will still require an additional alignment pipeline with all the different problematics that arise, like, for example, the scale, like metric scale, and so we also need to register the images each other, so on. So maybe we also lose some of the advantages that panoramic images have. Another point is that, as we'll see shortly, a single panoramic image already contains enough information to reconstruct their environment and so on. Compared to the pixel-wide depth estimation, the recovery of the 3D layout presents different challenges. So the first problem are the occlusions. We can have two kinds of them: occlusion from the clutter, that is the furniture, the objects, and also all the movable objects masking the underlying structure, and even the self-occlusion itself. Here is marked in red, where the structure itself occludes some parts from the single point of view. Furthermore, we have also other problems more or less common with depth estimation, typical of indoors, like texture-poor surfaces, where part of interest are less visible, or even particular materials. To this end, completing such reconstruction needs for specific indoor priors is necessary. And we have, as we have seen in the previous session, so we are going to combine that depth learning method with geometric prior applying. So we start from the basics, from the early methods. As usual, many fundamental priors, in fact, come from early perspective approaches. Two main concepts in this regard are the geometric context and the orientation maps. In the case of geometric context for an indoor scene, related approaches try to automatically label as floor, ceiling, and wall or object image patches, and then try to find the cuboid of best fitting of the room. Under the same priors, other methods introduce the orientation maps estimated from the Manhattan word vanishing lines from the image edge map. Here we have two fundamental examples about that. Such work also introduced the concept of indoor world model and geometric reasoning. Indoor world model is the same we have seen in the previous section. And in order to represent the indoor scene as a set of Manhattan world planes bounding the room, such approaches try to rectify in some way the original scene. In the same period, even Lee introduced the orientation map, but combining both the geometric context and the orientation maps itself. Such concept of geometric context and reasoning are then applied to panoramic images. One important work is panocontext. Panocontext, which converts a panorama to perspective views and apply the geometric context and orientation maps to recover edges and Manhattan aligned surfaces, and then project back the results to the panorama. Here we have an example in the figure. Panocontext for the first time evaluate also the advantages panoramic images for indoor reconstruction. Furthermore, this work introduced a pre-processing method to align 360-degree images to Manhattan axis. So try to greatly simplify the reconstruction. Such approach consists in transforming equirectangular images into perspective tiles, applying geometric context orientation map detection, converting back to sphere the results, and then the output of panocontext is a 3D bounding box that tries to fit such orientation, Manhattan-oriented planes. The same use of geometric reasoning is also exploited to improve room reconstruction from a point cloud, as in the other example here. In this case, applying the Manhattan word prior, and also tried combine point cloud and the structure classification in the image in order to complete the 3D point cloud. So going in more detail, even other approaches try this path. So geometric reasoning typically recover low-level 2D features like superpixel and edges, like in the work you have seen in the previous slide. And then they exploit indoor geometric reasoning to fit them in a 3D structure. Some methods embed Manhattan world geometric context and orientation map into the superpixel, transforming such patches into 3D facets, like in the example of Young here, and then fitting in a 3D mesh of the room layout. It should be noted that such approaches are not deep learning approaches. Okay, they are based on heuristic and geometric reasoning. The other approach here instead transform in a top-down floor plane domain the superpixel and the edges to fit the most likely room footprint, and also to find the layout height. Like in this way, simplifying the reconstruction. That is very similar to the diffuse architecture we have seen for the depth estimation in the session before, where we have one branch for the perspective analysis and one branch for the equirectangular analysis. In this here, in the case of layout, we need just the perspective branch, because we are interested just in the shape, not in recovering the Olmsden's depth map. And of course, this kind of approaches can actually be easily adapted to deep learning architecture, which in fact has happened. In this case, the features of interest are directly derived by a neural network, like in the priors, as we have seen, that remain valid also for deep learning architectures. The data-driven approaches lead to impressive results in terms of accuracy and speed, although they need a very large amount of annotated data sets. The typical outputs of such pipelines are not directly the 3D model, but they are usually room corners or boundaries like edges of surfaces. Indeed, such abstract representation needs some manual annotation. In other words, if you want to have a large-scale data set for training, we need also to annotate in some way the images. Like for it's more complex than the depth problem, because for the depth we can also exploit instruments like depth sensor, laser scanning, and so on to obtain ground truth metric measure of the depth. In this case, the layout is an abstraction. The layout of a room depends by the architectural design. So some kind of manual human intervention is needed in order to obtain ground truth. In order to have a fast and accurate ground truth, annotation tools are often automatically assisted, like for example, PanAnnotator, used for several important data sets. In this case, the annotation is performed on rectified images so that edges and boundaries are canonical, that is Manhattan axis. And for this reason, many important public available datasets are Manhattan axis aligned. And this, of course, affects even network analysis. A very common pipeline for layout estimation includes an image preprocessing model, which warps the equirectangular images to make it aligned to canonical axis. This will ensure that wall-wall boundaries are vertical lines, like reducing errors when converting from 2D to 3D. This is very important. And starting from the rectified image, a depth network predicts the fundamental elements representing the layout as tensors. Such tensors basically are corners or probability maps in image space. The final step of many pipelines is then a post-processing step. Out of core, this post-processing step is a kind of out-of-core step with respect to the network. This is very important. This also requires more computational cost, and which usually is used to regularize the network output according to the indoor priors. The post-processing aggregate and transform the tensors to recover the 3D model itself at the end. Here we have some example of image preprocessing. The main goal of this task is to improve the matching between the equirectangular pixel, which are view directions, and the geometric elements. A typical benefit of this step is that once the eye of the camera is known, 3D points in the floor or ceiling can be associated to the given view direction, but only if the room is a Manhattan of Atlanta world. So two kinds of pre-processing are common and also sometimes are adopted together. The first one, already seen for panocontext, is to wrap the input until wall-to-wall boundaries are vertical lines. The of pre-processing is instead to project equirectangular image to ceiling and floor plan, so that the resulting perspective image are almost distortion-free. Should be noted that to obtain a reliable projection, the warping of the panorama is also needed before. So in some way, such kind of pre-processing are are linked. Here we can see why images need to be so aligned. The point is that the trigonometric relationship between angles represent in a 2D map as 3D points, also if image lines are aligned at least to the horizon. For this reason, the basic assumption for indoor reconstruction in a equirectangular space that the image is captured around. That is, vertical lines in the image represent vertical lines in the 3D space. This assumption is less restrictive than full Manhattan alignment, of course, as well as it's usually already verified by a rational capture, as for example, common hardware exploit inertial sensors to produce an already rectified image. And starting from this preprocessed image, common deep learning pipeline is here. More here we have several examples, and we expect as input an already aligned image. So an equirectangular, for example, or the ceiling or floor projection. The network scheme is the typical encoder-decoder scheme where a contractive part reduces the image to a bottleneck. Then a decoder usually expands the features to reach the original resolution. The output of the network is usually a map which contains an equirectangular format, corners and boundary position, or a 2D floor plan with a wall. As a consequence, even the ground truth is encoded like this. So often a set of corner image coordinates or a probability map. We'll see more in depth on prediction pipeline next. Okay. The last step before some example is the regularization process in order to deal with noisy and incomplete shapes. A typical approach assumes the room shape as a 2D projection on the floor plan, of course. Here we have some approaches. In the first case, the Dulanet, the wall segments are regressed and clustered into horizontal and vertical lines. In the second one, the HorizonNet, the wall lines are fitted starting from corners position with a voting scheme based on ceiling and floor boundaries. Finally, in order to define the 3D layout, it's common to perform an extrusion using the layout height, which is a single indoor Atlanta models or multiple values for the vertical walls models. Should we note that the regularization, which usually complete missing parts, like the auto-occluded structure, is not data-driven. It is still in many, even in the latest solution, this part is not data-driven, but it is a post-processing out of the box. Here we present some pipelines. So an example of solution that try to address both the problem of too restrictive priors and the spherical distortion. This example is called AtlantaNet. As the name suggests, it exploits the less restrictive Atlanta world model, in which the environment is restricted only to horizontal floor, the ceiling and vertical walls, but without limitation on the wall shapes. So supporting, for example, non-right angles, curved walls. In this approach, the equirectangular images is encoded as a true horizontal projection. So encoding the room layout as an undistorted 2D footprint and the 8th value. Assuming the Atlanta world model, we project the panoramic image on the ceiling and the floor horizontal plane. This projection function that is called in the paper Atlanta transform maps all the points on the equirectangular space in the 3D space as the height was fixed was H and F here. The height of the floor, that is the distance between the eye and the floor. And consider we know constant and most fixed the height of the eye is a scale factor. The 3D layout of an Atlanta model is fully defined by the two-dimensional shapes, the 2D footprint of the layout and the ceiling distance. As a consequence, the height of the room is determined by the ratio between ceiling and floor shapes. Ideally, so in other words, we encode the height of the ceiling, that is the height of the room, in the ratio between the ceiling and the floor shape. In this way, we have only one branch to solve our problem with a depth learning pipeline. Ideally, the ratio should be the value that make the floor space match with the ceiling shape. The network architecture takes as an input the RGB projection. So in order to capture both the low level and high level feature, we keep the last 4 feature maps of the encoder. So each feature map is then reduced to the same size through a sequence of convolutional layers and then reshaped. The 4 features maps are concatenated to a sequential feature map. So we feed such a sequence to a RNN, and then we upsample such map to recover a binary segmentation mask describing the ceiling and the floor shape. Also here, it should be noted that in the case of direct feature fusion is not possible. So it's not possible to fuse directly ceiling and floor, since this will imply that the prior knowledge of the scale factor between the two transformer tensors that are different, because they are not, we don't know the scale, because to know the scale, we need to know the height as a prior. We don't have this. So itself, also the scale between the features is a known value. Train this network, so a specific loss function based on the binary cross entropy error and also the gradient is adopted. At inferring time, instead, the same trained network is applied to the ceiling and the directly. So the same network is able to predict both the ceiling or the floor, depending on the input. The input may be the ceiling or the floor projection, once they have transformed from the equirectangular images. So the 2D room layout is obtained with a simple polygonal approximation of the ceiling shape contour, which is less affected by clutter. And also, as we have already tell, the IHNR, the ratio, is obtained from the ratio between the contours of the floor and the ceiling, the shapes we have inferred from the network. So we build the final 3D model just extruding the footprint with the layout height. Here we have some example of public data set used and benchmarked with these methods and some reconstruction, including also custom data set with annotated 3D layouts having less restrictive assumptions. For example, rooms with carved walls or no-right corners, taken here from Structure 3D and Matterport. Everything is fine. I'm hearing someone. Okay.
Yeah.
Okay.
I wait at the door.
Okay. So more recently, 3D solution for object surface reconstruction from monocular input have been emerging for generic shape objects. These methods, of course, can be applied in indoor reconstruction. In order, the point is how to try to associate such methods to an indoor structure. So we have seen the data-driven solution of object surface reconstruction basically work from the outside of the objects. In our case, we have images, panoramic images taken from the inside. So we try here to show an example of application of such methods in the indoor context. Here, the model of a room is an arbitrary shape, and in order to fit or indoor structure to the we have to represent the room as a watertight mesh. The pipeline here in the example is called a deep 3D layout, and basically deforms a watertight 3D mesh that is a sphere as an initial object to approximate the room shape. As a result, the method generates 3D meshes for room not limited to Manhattan world of similar assumption, like curved walls, sloping ceilings, but even domes or other complex geometric features not handled by prior methods. Deep 3D layouts define the indoor layout as a 3D graph encoded object. So, exploiting in this architecture, the graph convolutional layers to infer the room structure as a 3D mesh. Then introduces a novel way to associate the panoramic image feature to the 3D vertices in an indoor environment. That is the main idea. So it exploits the gravity aligned feature to efficiently preserve the receptive fields according to an indoor shape hypothesis, and also try to refine incorporating the feature in the graph with a self-attention approach. Unlike the static projection used for generic 3D object reconstruction, we spoke before, such an active element is very robust to indoor occlusions. Furthermore, in the same approach is introduced a domain-specific loss function that combines specialized data and regularization term to guide the reconstruction towards a plausible architectural model. Otherwise, we have the reconstruction of generic objects, since we also need, for example, sharp edges and flat walls, ceilings. So we need in some way to regularize the solution. But the main point in this work is that everything is not done by a post-processing step, but it's done by the network itself with a full data-driven end-to-end solution. Here we have some details of this approach. So we have that the environment around the viewer, I mean, around the spherical camera, is a closed volume of fairly, so this is bounded by walls, ceiling, and floors. So this is a closed 3D surfaces that is to a sphere in some way. So, and that can be represented by a mesh with a fixed number of vertices here in the example. And so we encode such a mesh in a fixed connectivity object. So the connectivity is the same of the sphere, but the vertices position the positions are deformed and moved until we reach the room shape. To increase the robustness, we employ a coarse-to-fine approach in which we first target the reconstruction of coarse meshes starting from the initial sphere, and then we refine in a second step the coarse mesh to the final one. Here we have an example of the sphere deformation until we reach the room shape. This approach starts from the assumption that in the indoor space, as in the previous work mentioned before, vertical and horizontal features have different characteristics along and across the gravity direction. In order to support an efficient pooling of the image features, we perform an isotropic contractive encoding, preserving the horizontal dimension, which we expect contain more information in some way. We reduce the size of the network in this way, so minimizing also the interpolation effects between world and image space. So we, in some way, we try to gather more information using compressed feature. Differently from generic 3D object reconstruction, where a static projection is enough for perceptual pooling, in our case, here we have to cope with major occlusion problems caused by a vast amount of clutter and by the structure itself. To solve this problem, we leverage complementary feature in distant portion of the image. So in this way, we exploit the panoramic projection rather than only using local regions like in perspective image. We do that, but learning a set of attention weight vectors used for important spatial feature, so exploiting a self-attention scheme. That is in some way a kind of transformer, but not image transformer here, but transformer applied directly in the vertices, for the vertices and in feature space. As I have already said that we also need to make such a structure more indoor. So deep 3D layout here combines data terms for measuring the quality of fit for training data with regularization terms for driving the solution towards a plausible room shape. In particular, we expect that the models, as most human built structure, will be composed of large, smooth surfaces, not necessarily planar, and joining at possible sharp edges that is typical in architecture. Such a characterization is less restrictive than typical indoor prior based on planar surfaces and forced vertical and horizontal alignment in some way. Here we have some details about such data terms. Positional and orientation data terms, usually in 3D reconstruction, are computed by uniformly sampling the ground truth and the predicted surface meshes and summing the contribution at each point of the resulting point clouds. This term is typically bidirectional. For thermostats, we target a low polygon reconstruction in order to preserve also the relevant sharp features. We want to drive the vertices in the prediction to snap to ground truth feature edges. This is done by extracting from the ground truth meshes the feature edges. Okay, here. And why? Because if you use also only the data terms, the network may generate a very large deformation, and we need to deform a lot to closely fit the ground truth. This is harmful, especially in the first training iteration, where the estimation is far from the ground truth. So large vertex movement would compute inconsistent solution, letting the optimizer stuck in a local minimum. So we introduce regularization losses to drive the solution toward a plausible room shape areas where the data terms provide very little information. In particular, edge regularization is used to favor a uniform distribution of vertices, while an indoor-specific smoothness loss penalizes low curvature vertices, forcing them to lie on a plane or on a constant curvature surfaces. While we try to avoid to penalize the feature vertices with a more marked curvature, essentially. And here we show some example on public data sets. This is visible in the qualitative results presented here that contains concave rooms partially visible from a single point of view, or like non-monotone word corners like carved walls of ceilings. The solution is clearly promising from a theoretical point of view, but has also several practical limitations indoors. First, it's not obvious how an indoor structure, even of a single room, can always be represented with a closed and watertight mesh. The mesh model also is not really structured, and unless further processing and simplification are made, it's not easily possible to decompose it into walls, ceiling, and floors, and in general, in a well-defined structural boundary. This limits its use in various applications, of course. In addition, the GCN are, by their nature, not very stable. So the process of training them is not trivial and also has little scalability and interdomain usability. To this end, recovering the room layout by EV priors and occlusion is still an open problem. Several solutions, even very recent, also in this last CVPR conference, several solutions exploits geometric aware transformer that is similar to the geometric transformer we have seen, and also are being implemented recently with more effective solution than those based only on LSTM or multi-app self-attention, like kind of transformer that are basically image transformers. Can be a cascade of local and global encoding via Windows block of different size. In addition, geometric type losses on horizon depth normals can be used as in the example of LGT-net. In one very recent work here, the .NET, the concept of one-dimensional compression is expanded and separating the feature to be compressed according to both the horizon and also vertical planes. In this way, they try to improve the detail recovery that are usually loosed performing only horizontal compression. At the same time, the fusion between multi-scale features is also revised via a gated system, and also spherical convolution are combined and applied for the depth estimation, because especially for the here in this work, depth estimation is applied to estimate depth on the horizon in order to complete the layout with the geometric information. However, it should be noted that pre- and post-processing, not data-driven, as seen previously, are still necessary even for those latest works. Now, to summarize, we have seen that room layout reconstruction task, that is recovering the bounding permanent surfaces on an indoor structure, is still an open problem. This task is basically recover 3D elements from 2D features. Okay. In the panoramic world, single room layout is usually obtained from a single image, because IMSIM contains potentially the information of many perspective views, except for the parallax or the depth, of course. However, many open problems are still open research. For example, the occlusion, both for crater or also from the structure itself. To this end, almost all methods still adopted very restrictive pre- and post-processing priors and steps to regularize and integrate the missing parts in the data-driven results. Another important problem is the output model. Real indoor structures are hardly represented by continuous edges or corners, or also with closed meshes. And so even the most complex structure based on meshes or combination edges and meshes is very hard to be segmented into a structure. The next session, okay, we'll investigate how to complete such reconstruction, also how to investigate how the information collected from single images, that is the pixel-wise and layout reconstruction, can be exploited to model a more structured and complex scene since arriving to a 3D scene. So I don't have the Vancouver time here. I don't know if
So it's 10:30. We are perfectly in time, more or less. I don't know if we're gonna have a short Q&A session now, since people is, the attendant, they have a fresh memory of the topics of these talks, or we will have a longer Q&A session at the end of the tutorial.
Normally it was planned to have a longer session at the end to allow you to have a break, but you may decide, because I think the time
probably would be better.
okay.
Yeah, we start a Q&A session now.
Okay,
so I don't know if there are questions in the chat. I see one message in the chat. No, this here nothing. Yeah, you can.
Thank you for the talk. I would like to have a question about the room representation. So for room representation of 3D layout geometry, I would like to hear how we can reconstruct 3D layout geometry with different ceiling height. Because most of the models like Horizon Net, Let2Net, and still the state-of-the-art models are considering the 3D layout geometry with a constant height. And even datasets like Zillow dataset, the Grand True labels are considering camera height, a constant camera height. So I would like to hear some thoughts about how to estimate the camera height. And that will be one talk. And another talk is I would like to hear also some thoughts about open areas. In indoor environments like this one, we can see a clear structure where we have a clear limit of where is the walls and how is the geometry of the room. But in modern environments, we have open areas where it's not clear where some area is ending and is starting another one. For example, like a kitchen that is open. So we don't know exactly what is the limitation of the kitchen and the dining room. So how to define those geometries and how to reconstruct the 3D geometry in those specific open areas.
I think I will give the floor to Johnny to answer.
Okay, yeah, okay. Okay, starting from, see different kind of ceiling, different levels of ceiling. So actually is a limit of current data set, as you said, but novel data set, especially novel rendered data set like replica and so on, are trying to combine even more complex shapes for rooms. So, but this is still an open problem because this is clearly affects also the results, because we are still, especially for supervised reconstruction. Okay, is this still a limit? Actually, deep 3D layout faced this problem, so we also released with the paper, which is our data set. We also includes more complex shapes for the ceilings. But also we understand that it's not easy. As I have mentioned before, it's not easy to annotate such kind of data. I think that a good solution will be a synthetic data set where we have a very accurate layout, a very accurate annotation or abstraction of the layout, even for more complex structure. Otherwise, it's very hard to annotate the ceiling, annotate the structure, especially if they have ceilings. And also just connecting to your other point about the to define where the room finish or where we are connecting to room, or what is the concept of scene that you are reconstructing. Now we are strictly related to the data we have used for training, but as we are going to see in the next session, will be also possible to solve this problem, to combine more than one image and then apply some kind of semantic segmentation in order to decide where or a scene of interest finish if you are just seeing one room or we are seeing a bigger space and so on. And also the other point about the eye of the camera, okay, it's usually given as a scale factor. So usually they assume that the camera of the same dataset are acquired from the same height. So this is affect just the scale, not the accuracy. The problem is that we are going to combine more than one image. So we also face, we also address the problem of having cameras that can have even a slight difference in height. So also there we need also to deal with a more accurate measure or estimation of the mutual position. We'll see this point in the next session. So about combination of more than one image. And basically, they are all three limits of the single image reconstruction and so on. I don't know if my colleague wants to say something about that.
Oh, I think if I want to say something, I think that one thing that one has to understand, especially in the examples that were discussed in this session and a bit less in the next session, is that the target of much of the research has been to do what we can do best with a single image and what we can do best for a set of environments that are common. It's obvious that there are many environments that do not match the assumption, but this is basically one of the points that probably will come out from this tutorial, in the sense that the idea of priors and the priors that we have force some solutions and also force the environments that are handled. The fact is that in practice, for most industrial application and so on, common environments match mostly Atlanta World or similar environments. You cover a lot, okay? So it will not going to be working for very complex things with carved walls and everything, but we basically cover many things, okay? So the solutions here try to do the best that you can do with within the priors. And there is no solution right now that works in general for any shape, okay? But these are models of industrial interest, okay?
Okay,
Thank you.
question. Another question is coming.
Yeah, I'm new to this domain, so I'm curious about evaluation, especially if you have furniture, also moving objects like person. Do you consider those in the ground truth? What are the metrics for evaluation? Thanks.
The metrics for evaluation of the methods that you are considering.
The metrics for evaluating the accuracy?
Yeah.
There are several, I will also let Johnny discuss, but there are several standard metrics to evaluate the accuracy of the reconstruction that are typically used in the various applications, and also depends on what you are reconstructing. If you are reconstructing depth or you are reconstructing layout or something. So, for example, you have a matrix of intersection over union that you can have, especially if you use layouts, metrics that deal with average depth, average dimensions, so RMS errors and so on. Typically, most of the papers that you will see use some set of standard data sets to make the benchmarks and the same set of measures to compare. Okay, so I don't know if Gianni wants to add, but basically, if you look at any of the papers, you will see the same set of measures that range from differences in geometry, like average deltas, percentage of errors, percentage quantiles, and so on, and the intersection over union.
I don't know if Johnny wants to add something.
Yes, the same Enrico said about pixel-wise error metri. I mean that error for that. This is measured over a ground truth that is usually measured with instruments. Okay, so we have a metric ground truth, all for synthetic scenes. We also know the real pixel-wise dimensions, so we compare with that. From the layout accuracies, it's more complicated. As Enrico said, we use intersection of a unit and so on, but we have to consider that layout is an abstraction and usually come from a manual annotation. Okay, so that even the error depends by the specific data set.
Okay. Another question. I think that after that we will go for a break because otherwise we will
have a short break. Okay, and then we can.
Yeah.
Hi, thank you for the talk. I had a question about the data set. So the data set here is mostly finished homes and pretty neat data set. How do you think these models adapt to something unstructured like construction sites, maybe?
That is a good point.
Could you repeat, Marco?
Sorry, can you repeat? I didn't hear.
Yeah. I mean, he's asking about how these methods could adapt to construction sites. So it's like, you know, in indoor that is not yet completed, you know, it's like under maintenance, you know, this kind of environments.
Of course, yes. But in some ways it can be also easiest since we have less clutter in construction sites. We have, of course, we have other instruments and so on, but okay, yes, it's possible. And also there will be also, because it's very easy to make an acquisition campaign based on panoramic images. So it's a good point, of course. And perhaps we can also, I think also there are also companies that already are doing this. I don't remember the name, but there are many important companies that already sell such kind of service. Okay, so using to monitor the construction, building, and the inside operation. Okay.
So I think that we can have a break now. Let's say 10 minutes. Enrico, what was the expected as for the break? 10 minutes?
Well, the expected time for the break was before the Q&A, so I mean it's okay. I mean anything for us. We are at home, so we can do whatever.
Just need to set Vancouver time here.
10 minutes break from now. So let's meet.
So we reconvene here in 10 minutes, so it will be okay 7:50 for us and
10:50 here. Okay. Thanks again for the attendance, and thanks Enrico and Johnny for the talk.
See you in 10 minutes. So
see you later.
The second section to this, right?
Yeah, second section will be about the integration of, you know, the room, how to make a structure, and then how to explore them and to modify the.
Yeah, this is a really interesting me. So I work for open space.
Oh, wow.
Yeah. So
Yeah.
so I don't know if you've heard of us, but
Yeah, of course. Do you also use, like, you have a lot of data?
we have tons of data. So we get like
with that panoramic image, so.
panoramic image. So we use all the Insta cameras, Ricoh cameras.
Oh,
So our company, they install the cameras.
but you also have AI solutions already integrated
We
in
do.
your pipeline?
We do.
Probably you implemented some of our stuff.
So that's kind of what I wanted to ask, right? So like applying ML in these areas is kind of complicated. So, we've tried hard at semantic segmentation and all of this.
Oh, segmentation is actually still
Very,
an open
yeah.
problem, it's like.
So I did try like OmniDepth and all of those kind of stuff for the depth estimation stuff, but they don't seem to generalize that well. And also like the
Oh, yeah, I get it. I guess.
hence
Yes,
the question about
It's like I said, it's like, that's like, probably is for most of the things that you see in CVPR,
right?
The real world.
The real world. Exactly.
This is something here.
So when only half the world, walls are
Well, what's like in the remote solution is, probably the solutions, they could be, good enough, and they need examples.
right, exactly. So the problem is,
But for putting examples, you need the resources.
yes.
It's like, so I would expect, a big
Yeah.
company like Google put together everything I saw. I mean, I will talk a little bit about at the end, really at the end. That is like a few days ago, it's like, they announced that there were companies that are creating home GPT.
Right. Wow.
Yeah, you didn't see it.
No.
I think it's like a few days ago. It's like it was open. OpenGP. You put the picture
Yeah.
in the system and they propose different kind of visual staging, different kind.
Right. Wow.
So,
I know.
that's the future.
Yeah. I mean, for us, like data isn't the problem. Like we get like thousands of hours of video every day from all around the world. It's a problem of like the labeling, right? Labeling these images is really hard. And you end up kind of going into like that cubic projections and then doing stuff and then, projecting it back. So it's kind of hard.
And also from compatibility is very high, very time consuming.
Very time consuming. Yeah. So,
It's like this is something that, will, I mean, it's like, in my group in collaboration also with them, and we will try to address how to try to improve the semantic segment. But the problem is also, I don't know, it's like he is already mentioned in the previous talk, but we will mention again in the future is the problem of the resolution of these models.
right.
It's like, you have pictures that has like,
4K.
I have a ladybug camera in my office, it's 8K.
Right.
And then, but then you need to do processing to 1K.
Yes.
That's, and
Yeah.
then we needed to get back to 8K in theory. It's like, especially if we go to a very accurate semantic segmentation, this is not really.
Not possible. Yeah. So,
Okay.
interesting. Yeah.
See you later.
Yeah.
Adrian.
Sorry, just a quick question. How can we get access to the recorded session?
I don't know. Actually, it's something, this started automatically when we had the Zoom meeting.
Okay.
Yeah.
So, is there going to be a link or something?
Hopefully.
Okay.
Yeah.
And to check that, how do we know?
I think I will ask you probably send a mail to the, to the, CVPR people.
Okay, so CVPR will organize
I
the.
think it's so because they gave us the Zoom meeting and automatically the recording start.
Okay, so they handle.
We cannot even stop. We don't have.
They manage everything. Okay.
Hopefully. Then of course we'll manage to.
Okay.
We'll try
All
our
right.
best.
Fingers crossed.
Yeah. Cross crossing. Yeah.
Okay,
Thank
very
you.
much.
Mm. 1 minute, and we will start.
Excuse me, sorry, what time are you starting again?
I will start in. We'll start in 1 minute.
Oh.
Okay, I think that we can start with the second part of the tutorial. I will give the floor again to Gianni, who will talk about the integration of multiple panoramic images to create the integrated indoor model. So Gianni, the floor is yours. You can start your presentation.
Okay, now can you hear me? Yes. I guess yes. Okay. Also, the information collected from single images, that is pixel-wise and layout information, can be used directly to model a scene or integrated between different images. Okay. So, okay. And to model a complex or the more structured scene, we expected to have as input individual rooms models or dense information like depth maps. Primarily in case of many images, camera position, and even multi-view feature are expected as input. As a result, we expect to model more complex scene or even to improve the single room accuracy, overcoming, for example, the structural occlusion, or also solve the problem of have two rooms joined on just one door, or even more complex environments. A common target model is of this kind could include a segmented floor plan, structured, for example, into rooms, and also with panoramic visual information associated. It should be noted also that in this course, we don't cover, for time reasons, object detection, recognition. In general, all about total scene understanding, which is for some aspect topic by itself. And fundamental prerequisite here is the image registration, that is having the pose of each image in the same reference space. However, we'll see how this is not very strictly required for modern data-driven approaches. This context, we have three fundamental tasks that are usually addressed. The first one is recover the indoor structure by integrating single view analysis, usually from very few shots. This is a common case that is in practice a typical case where panoramic capture give all its advantages because we exploit just very few shots to acquire very large and structured environments. The output can be a single scene here, but better detailed and reconstructed from multiple views, or a multi-room structure itself. Sorry. Okay. The second case instead, okay, we have spoken about sparse capturing, but here is a more specific case. If you have a dense input acquired, for example, during a professional acquisition campaign, so the main problem here is to segment this data into rooms and starting, for example, from a dense occupancy map. Also, we have the combination of these cases where that case involves the integration between structural geometry and visual data, and combining also multimodal information in order to build a visual integrated model, as we are going to see in the next section. The second case of dense acquisition is a more classical task that is very similar to geometric indoor reconstruction from the generic dense point cloud, for example. The first and the third are instead more computer vision challenging problem. Starting from the first case, the results obtained from a single image can be combined in order to complete multi-room and very crude structure, but before data-driven approach, we have several exploited multi-view to recover images, position, and 3D clues. Here we have some example in the work of Cabral and Furukawa. For example, we have geometric reasoning on a single panorama or single panoramas exploited to integrate a pre-calculated point cloud. Here they adopt a Manhattan word piecewise planarity assumption, exploit image data to complete the hours in the point cloud. The second example, instead, 3D faces are recovered from a superpixel segmentation of multiple panoramic images. Oh. Such images are registered in a common floor plane space. They assume here only vertical walls, so they can reconstruct also sloped ceiling and walls with no right angles. In this work, 3D information is recovered directly from image registration, and the spatial transform is applied locally to each superpixel in order to transform each superpixel in a 3D face. So 3D faces can be, from different images, can be joined together to obtain the floor plan. However, such approaches have many limitations. First, the image segmentation, even based on indoor geometric reasoning, and it's also based on empirical and heuristic criteria and thresholds. So results at image level were not robust. So as a consequence, reconstruction was led by 3D data and requiring a very dense coverage of the scene to achieve satisfactory results. As for the single scene case, modern data-driven techniques lead to novel and effective approaches here. For example, they use the computer vision technique to use a less number of images, and also with less computation, and also obtaining results with easiest campaign. Such techniques are effective even in case of sparse image coverage. It's the typical case of the commodity panoramic acquisition. Furthermore, all the techniques seen for the single image prediction can be exploited also here in order to merge in the results. The monocular layout estimation technique are less effective for large open spaces, as in the question before about spaces that are open or complex connected rooms with self-occlusion. The typical statistics, also in this paper here, limits the use of single images when over 10 corners. And also, there are many limitations for multi-purpose environment like living joined with a kitchen and so on. To this end, many works try to join multiple views, even to reconstruct a single room or a single structured room environments. The common case is to use a couple, just two rectangular images scenes to cover a complex scene. We have a wide baseline, and the alignment between images will be noisy. And so also the layout from a single pose will be incomplete. Typical solutions is to try to find a mutual pose and the full layout jointly. Here we have a more detailed example. Such pipeline combine many techniques which we have already seen from the single image layout. We have created a network in order to refine the pose estimation and work in the transformed space as seen with AtlantaNet. Then to predict the layout, two branches are exploited. The first one works in a rectangular domain following the same baseline of DulaNet. The features are extracted by a ResNet from both input images, then features from image 2, here in the example, are projected in image 1 using the mutual pose. Features are then joined through a cross-attention module and transformed in the projected floor plan space. In parallel, the images are transformed in floor space, and the second is projected to the first, so the mutual position are compared. Since the feature both branches are in floor plan space, can be joined and decoded directly to find the footprint mask as in AtlantaNet. Here another possible approach for joined pose and layout prediction is based on a single rectangular branch. Instead, the residual feature is extracted from the two images and feed to a vision transformer in order to obtain a set of horizon feature. In particular, the transformer module has a multi-head output, returning horizon ceiling floor coordinates from which two layout depth maps are estimated, and also return horizon co-visibility and correspondence maps. Such maps are then fed into a post-processing pipeline to obtain image pose through a ransack, so not data-driven, is post-processing. And given layouts and poses, the final layout is obtained just by a simple merging. Here we have another case of layout fusion from sparse input. Such approach also combines more rooms and simply combines monocular layout estimation, multi-view stereo network in order to obtain an accurate 3D layout of a scene on a large scale. Each panorama is treated as a reference view, compared to a set of associated near source view. Then the layout is represented as a set of 3D planar elements. Furthermore, the semantics and self-attention are adopted to enforce the structural analysis. Here we have more details. A 2D layout is estimated in image space as boundaries, a classical elements are fitted through an homography, Manhattan World, into 2D layouts to compute a cost volume. So they compute a one-dimensional probability map for each layout element, and then they found the best layout for each room. Technically, they build a layout cost volume from layout homography, just compressing the volume into a one-dimensional probability map, and regressing a single depth value for each layout element. So they adopt a kind of one-dimensional depth encoding. As a result, the final 3D layout is just estimated, minimizing the cost volume and eventually aggregating with other rooms near. So, previous mentioned methods usually assume 2 images per room. Okay, but So allowing the typical multi-view layout registration, typical of structure from motion. However, this is possible in case of professional acquisition campaign or semi-dense acquisition campaign, but actually capturing that is provided by a non-professional user has usually less images, with some rooms that are covered by just one image. Such sparse coverage makes hard for static from motion to detect the relative panorama poses. However, this step tend to fail also for a sparsely captured panorama with a wide baseline. However, it's also possible, also in this case, even if extracted from motion doesn't work, it's possible with panoramic images also to obtain a compelling reconstruction, as we are going to see in the next slides. Here we have an example of layout estimation, extreme structure from motion, where we have an example of layout estimation, image registration, and multi-room floor plan arrangement in the same pipeline. It should be noted that in this case, the structure from motion fails, even aligning two images. So for each panorama in this work, they estimate a room layout and detect the door and the window position by using a standard neural network method. So after they reproject the information into a nadir, that is a top-down view like for AtlantaNet view, so they generate an arrangement candidate based on the door's connection. That is the same concept of the structural indoor model we have seen with Enrico in the beginning. So they finally use a convolutional message passing network that is used to evaluate the realism of feature. So the output is represented as a 2D relative camera poses. That is the position and the heading angle for each panorama. So in the previous section, we have investigated different parts in the challenge scenario of a sparse panoramic coverage of a floor plan. However, now we can take a virtual break from sparse coverage, and then we are going to complete the floor plan reconstruction, even speaking about of a more dense coverage. In this case, the problem becomes quite different. So in the case of a professional acquisition campaign, we have usually as a dense point cloud, so a density and occupancy dense occupants maps represented usually as a floor in a floor plan, a nadir plan. So for each pod, we have a dense depth map that is associated with the RGB image coming from a sensor or from the methods that we have seen in the previous section, for example. And also we assume in this case to have a smaller baseline between images. So it's possible to be that the point cloud and depth map can be aligned through the structure from motion or IPC method. So as output, instead we expect to obtain a top-down floor plan map of the indoor space with segmented rooms. However, so given this representation, 3D rooms can be extruded assuming indoor priors. It should be not that segmentation here is a fundamental task to obtain the file structural model. Since we have a lot of data, but we don't have any partition between the rooms. So the typical structure is to obtain the rooms as a connection of nodes in a graph. In this context, the early approaches try to segment the rooms clustering in space according to the free space evidence. Sorry. However, this is a typical problem that you can also solve with a data-driven solution. We are speaking about segmentation of 2D map. So such approaches start to combine heuristic approaches, geometric reasoning approaches to segment the floor plan with the aid of data-driven parts step. Here is the case of floor plan, floor SP. Floor SP is a hybrid approach. The method starts from the room segmentation using general purpose semantic segmentation technique like mask or CNN. The room segmentation reduces the floor plan graph inference into the reconstruction of multiple polygonal loops, one for each room. Here we have in the second figure, and the room, in order to complete to optimize the polygonal loops, they adopt a room-wise coordinate descent optimization in order to obtain a room structure one by one by minimizing the sum of data consistencies and also the model complexity terms. And finally, a simple graph merging operation combines the loops into a floor plan graph structure. Here we have another example, even more recent, about another hybrid approach. It's called Monteflor. Monteflor starts from the room proposal from mask CNN, from the density map. In this case, room shape proposals and their combination are detected using Monte Carlo tree search algorithm according to an objective function that combine a metric score predicted by a depth network and regularization terms. This network takes as input the density map and an image of the selected proposal to predict the intersection over union between the selected proposal and the ground truth. The regularization term encourages the selected room proposals to be in contact with each other without overlapping. And here we have another step. So more recent approaches try instead to have a fully data-driven pipeline. For the segmentation task, there are many general end-to-end solutions. So here they try to apply a single pipeline that using an hybrid approach to solve the problem. In this case, the state-of-the-art corner detector is applied to find room corners candidates defined as edges from a fixed number of uniformly distributed candidates. Then also we have a fixed number of true or false candidates in this map. We can apply a typical transformer approach. We have a fixed sequence and then we estimate from that a confidence map of the floor plan corners, refine it using such confidence map edges, and some candidates are extracted in order to model the walls. And they are not used directly as prediction, but they are extracted on the fly in order to train runtime and to train the network compared to ground truth. As a result, we obtain a floor map as a combination of edges, as in the figure here. So we know that we have a floor plan like the one we have seen the previous methods, so recovered from sparse or dense convergence, but we also easy from here to extrude a 3D layout, mostly applying the priors we have seen before. However, panoramic image integration can be enhanced in novel ways, especially by exploiting novel deep learning techniques. It can be useful, we'll see this also at the end of the talk, also to associate visual data to a geometric 3D floor plan or 3D layout. In this example, we represent a floor plan as a 3D extrusion. So we build a latent representation of it, sampling a fixed number of positions in 2D space. So we render from each position of the panoramic position a 3D rooms as a panoramic 3D layout. So panoramic 3D projection rendered of the layouts that we have from the extrusion. And so we encode each room as a feature vector. I mean in latent space. So we have a latent representation for each position. In the room. Position are spaced inside, as we can see in the last figure here, where we have floor plan and we have fixed position, where we have some renderings. So we have a latent representation of the floor plan. In a similar way, the single image that we want to localize in this floor plan is encoded as a feature vector. So this is encoding by a layout-to-layout network exploiting feature distillation. In a first step, the inference, we found a draft pose that is recovered by comparing the image feature in latent space with the floor plan latent feature using a simple nearest neighbor search. And finally, we have a second step where we refine the pose to a gradient-based approach. Such approach is still hybrid. So recently, the same authors transformed it in a full data-driven pipeline. Here the intensity map is represented directly as a latent floor plane, not decomposed in different renderings. And the individual renderings here are exploited just to train the latent floor plane estimator. So the image and the floor plan share the same latent space, which is imposed during image network training. That is, image layout is similar to latent floor plan individual layouts. The prediction is done in latent space directly, so without nearest neighbor search and so on. And they allot just a gradient refinement step as a post-processing in order to refine the position. This approach finds only the position of the camera as the previous one. So they assume that rotation, okay, is already known. Rotation is basically just one angle that the image is aligned to horizontal plane. But with an extension of this approach, it's also possible to add the rotation as additional parameter, and by comparing line of layout with the vanishing line of the image in order to also find the rotation of the image if it's necessary. And once we have the layout as a single or multi-room, an associated visual information, as we have seen, and also the final goal is to have a full 3D textured model. And as we have seen before, early approaches exploit structure from motion and superpixel segmentation. Then they use geometric reasoning and other heuristics to obtain the 3D floor plan. In this case, the 3D model is textured by just warping and splotting the original cluttered images, which are registered on the geometry thanks to the structure from motion. However, if you are, as you can see in the example here in the figure, if you are going just to texturize this way, such solution have a low dominant adaptability and robustness, okay, because are hybrid or even without data-driven support and depend by heuristic priors and thresholds. And also the visual 3D scene is obtained by also splatting the clutter and objects and things that are not represented in the 3D models, and as a result, we obtain many visual artifacts in our textured model. We have data-driven techniques, so obtaining a 3D scene from the simplified layout image becomes a specific topic. So in this approach, we assume that we already have the 3D layout that is obtained from dense or sparse coverage, single or multi-room, and also we have the aligned images. And so here we can also exploit, for example, CAD blueprints or CAD atlas from the objects, because of course, if you want to reconstruct a textured model, we have also to deal with clutter. So we have two ways. Or if you are, as you can see in the next session, we can empty the rooms and empty the images with deep learning techniques, or in some way we have to deal with some kind of object modeling. In the example here, a 3D floor plan reconstruction, we assume that 3D floor plan, the images are already aligned also. So it's not important if they are sparse or dense, so they are aligned with the previous method we have seen. And here the first step is to generate textures for the observed surfaces. I mean the parts of the image that are visible. So to crop the texture sample, they use in this approach semantic matching, and also they try to match structured part in 3D model to the image segmentation. So they have image segmentation and 3D segmentation that it's easy because they have just for label, walls, floor, ceilings, object. Then rectified surfaces are extracted from the photos in order to condition the texture generation and also to synthesize suitable texture sample with stationary statistics in the texture. They should be seamless and so on. So there is speaking about the visual part, that we have a network layer that is deputed to build the texture sample. As the texture of observed surfaces is done in this way, but the main challenge here consists in texturing the unobserved surfaces. That is, many occlusion we know dominate the indoor space, so image could not cover every place and every room, even with a dense coverage. So to this end, a possible approach is to propagate available texture according to room connectivity, in this case by the doors connectivity. In the presented approach, a graph neural network is adopted to represent the floor plan, where the rooms are the nodes and the edges are the doors. In this way, the texture samples are propagated according to the minimization of this graph. Here we summarize the concept we have seen here in this part. So we have seen as multiple panoramic images can be exploited to reconstruct more complex structures. Multi-view can be combined to recover more detailed layout or to model multi-room environment. Finally, we have seen how to associate visual data to geometric information to build a textured 3D scene. And several problems, of course, remains also here. For example, multi-room scenes are limited to heavy Manhattan word pliers. So solution is usually fine, in fact, in a 2D domain, and then the 3D part is extruded by this 2D floor plan. Also, multi-story, multi-floor environment or complex structures, such as, for example, stairs, pillars, are not faced by the current methods. And then, moreover, resulting 3D models lack many geometric details and many photorealism stuff. To this end, so to complete this also this course, this model structural model reconstruction. In the next section, we investigate more the visual aspect of the model and the photorealism of the model, with a focus on generating models useful for interactive exploration, editing, and the very common now VR applications.
Okay, thanks, Johnny.
Oh,
And now I will present the last part of I think that we will skip the last to the after the final. Okay,
Are the sessions recorded?
I think so. So, yeah. So, thanks, Johnny, and thanks, Enrico. And now comes the last part of this tutorial.
We see the presenter view, not the display view.
Oh, wait a second. I don't know if I can. I don't remember. Okay. Thanks, Enrico. So this is the last part of the tutorial, and this is related to how to explore these panoramic images indoor, and also how to provide a data-driven solution for editing. So I will more or less provide an overview of what are the current trends in these topics. It will be mostly related to how to integrate these panoramic indoor scenes into extended reality setups that are becoming again very trendy, and also how to use technologies for performing data-driven modification of the scenes for applications like virtual staging. So before starting the real presentation, I will mention something related to who is funding my mission, because this part of this tutorial is funded by a project that is managed by Qatar National Research Fund, that is related to the creation of indoor digital twins by using panoramic images. And all the work packages in the project are more or less mapping to the pipeline for automatic reconstruction, and also for creating interactive exploration and visual representation generation. So the partners of the project are Ahmad bin Khalifa University, that is my institution, CRS4, and the Qatar University, and also a big construction company that is called GHD Qatar. So these are for another. Then, for what concerns the introduction, until now, we saw how to manage and how to create, indoor, how to create, to extract information about indoor scenes, that it can be also pixel-wise information, or also layout information, or floor plans. Now, the part of this talk is related to how to do with this kind of information, how to perform editing, and how to make a immersive exploration that can be used in extended reality setups. And of course, you can imagine that there are many application contexts. I already talked with some of you that they come from, from companies that they are interested, in applications related to architecture or building or real estate domain. So you can imagine also that this kind of technology became very, very popular during the COVID period, because people could have the chance to create virtual tours for seeing, the real estate properties, and that, to have the impression, to have a clear understanding of how these rooms and how these environments look in real life. And also, of course, there are many other application domains that are related, for example, to tourism or for construction sites to follow, it's like to following the maintenance of something. So here in this slide, you can see, there is one project that is from a Metropolitan Museum to create 360 panoramic image to create virtual tours for people interested in artworks and so on. And for what concerns this part of the talk, the outline is like I will provide an overview of the state of the art and also some information about our recent contributions for the two main tasks that we can consider for interaction with the panoramic image. The first task is related to how to interact and how to be immersed in this kind of environment. And so I will provide some overview of related to some pipeline that we created by integrating deep learning models in a rendering framework that we just published. And also is something that is work in progress, but is very, it's like, is how to create automatic view synthesis for 6 degrees of freedom immersive exploration of indoor scenes with Atlanta work construction. And the second part of this talk instead will be related to how to make models that can provide the modification of the scene and provide the tools that automatize the editing process. So I will showcase an example of a model that is able to automatically remove all clutter from the indoor scene, so for diminished reality applications. And also very few information about work in progress that we have is how to apply photorealistic style transfer. So how to apply the style from one room to another room in a way to preserve the content of this room. So for what concerns the first part, immersive exploration, we can the goal is to support interactivity and support, to give the user the chance to feel immersed in the environment. And of course, there are many ways and many devices in which you can try and you wanted to exploit and to interact with the scenes, ranging from desktop systems that are more used by the professionals, for example, for editing and for CAD applications, up to mobile, because people, especially in the social media, probably the area they want also to showcase, these scenes to have a very fast way to interact with them, up to the extended reality setups that are, getting again trendy. Probably you heard about the recent presentation of the Apple device, and also yesterday I heard about the new AR augmented reality setup from Meta. That's like the ARIA project, and I will more or less detail something about what are the technologies that you can find online for viewing and for rendering these panoramic and scenes, like these sphere image viewers. I will provide some details about the underlying 3D geometric representations that are used in these viewers, like texture domes or cube maps or point clouds or tessellated mesh. And finally, I will provide also some information about the trendy enriched image representation that are becoming more and more popular, especially in this field that range from the multiplanar images up to the neural radiance fields that are nowadays super trendy. Even in this CVPR, there will be many interesting papers about that. And they are, of course, they are also you can see some solutions they are trying to work on indoor panoramic images. So for the first concept, it's like the technology that you can use and you can find, especially online, for performing the viewing of these panoramic scenes is currently more or less tending to use technologies like WebVR and WebXR and WebGL. So, they provide solutions that work on browsers. They provide direct integration with extended reality setups and VR devices. And here there is an overview of some of the most popular solutions, like the KR panel, or it's like, or for example, some Panelum, and they mostly use WebGL technology. They use libraries like A-Frame, and they give the chance to use stereo panoramic couples to have even the chance to have real 3D immersivity. And for what concerns the geometric representation, the most, the immediate one, the most classical one consists of performing a distillation of the spherical dome and to text-to map the equirectangular image on top of that. For creating a spherical dome, there are many methods. One of the most classical one consists of iterative subdivision. So you start from an icosahedron, and then you perform a subdivision up to the resolution that you wanted to have for the tessellation. For example, you can go up to level 8 in a way to have 1 million vertices, and then you can text to map your panoramic image in a way that you can perform automatic perform interaction by performing a rotation of your viewpoint to see the scene and to have various perspective projections of the scene. And another very popular representation that is used in viewers, in popular panoramic viewers like KR panel, consists of converting this equirectangular image to a cube map. So to a cube representation with 6 faces. And the popularity of this method stands in the fact that graphic hardware accelerates texture fetching in shaders. So, and this is historically due to the fact that these cube maps were very popular since, I don't know, maybe even more than 10 years for creating environment maps for games or video games. And they are currently used also for having a way to interact with these indoor panoramic scenes. And finally, you can manage to integrate various signals in this kind of representation. So you can, for example, integrate the depth signal that normally you have at a 16-bit resolution and represented in with representing scale about millimeters. So for indoor rooms, you normally have scenes that have maximum distance of 65 meters. So that is more than enough for most indoor environments, and you can use them for performing, for displacing the vertices of the spherical dome, or even for creating point clouds that you can use for interaction. So here you can see an example for indoor panoramic scene converted into a point cloud. And of course, you can also have a faster way to perform the projection and the perspective projection from indoor panoramic scenes by considering, by performing a single pass raycasting on screen coordinates. So you basically draw a rectangle or that is representing the viewport, and then in the fragment shader, you pass the parameters that you needed for performing the perspective transform. That's like the field of view or the distance from the viewing plane. And then for each fragment, for each pixel in the rectangular image, you cast a ray that is starting from the high position that intersect with the spherical scene. And with this ray, you use this ray for fetching the corresponding pixel from the signals that you have. In a way and for doing that, you also use inverse spherical mapping. So this, is used in very many viewers. Even this method is actually the fast way, especially if you have a good graphics card for performing rendering. And we more or less integrated most of these techniques in a framework that is also using some of the models that were presented in the previous parts of the tutorial, and is also using technology for performing entering of the room in a way to enable a simple virtual staging applications, so simple insertion of virtual objects in the scene. And for doing that, we integrated the models for recovering the 3D layout. So like the one presented by Gianni before, and also integrating the pixel-wise signals like the depth signal or the semantic signal for performing transfer between various scenes and between the various versions of the scene with clutter or without clutter. And these are some examples of what we can do with our framework, and we can have a version of the scene that is with a clutter and a version of the scene without clutter. And we can insert virtual objects. In this case, as a simple 3D graphics objects, but you can imagine that you can also insert virtual furnitures, and you can also transfer semantic content between the full scene and the empty scene. And finally, for what concerns the exploration of this scene and the immersive interaction with the scene, nowadays, the trend is to have data-driven solutions that are using image-based methods. And a few years ago, there's methods that they were developing the concept of multiplanar image were presented, and they were adapted to the panoramic image by changing the proxy geometry representation. So multiplanar images, they are images containing multiple that information that can be useful for performing this occlusion, especially when you want to have 6 DOF interaction inside the scene. So in case of the standard interaction, you are not allowed to perform translation of the viewpoint because you would see part of the scene that are occluded in a wrong way. So there's like most of current methods that try to address this problem, and they try to provide solutions that enable the users to perform 6 degrees of freedom interaction with the scene. And these solutions, they employ methods called the multi-spherical image. So they represent the scene as concentric spherical shells with different depth information. And they start with all omnidirectional stereo videos, like for the Matryoshka system that was presented a few years ago in CCV. Or in the same period that SIGGRAPH was presented a method from Broxton et al., the group of Debewerk, that is still using multispherical images and converting them to a layered mesh representation. In this way, they can provide immersive exploration of this scene, but at the cost of a very complicated setup for acquiring images or using videos and so on. So these solutions, they are effective but they need a lot of data, and they need a complicated setup for the acquisition of the images. And on the other side, recently, Whitehofer et al. Is like last year at ISMAR, they presented a solution that is using a multi-cylinder image. So a different proxy representation that is simple to manage at inference stage for the generating the view, for the generating a synthetic view, and then work on a single image. So this was more or less the first method of view working on single indoor image and performing a data-driven processing in a way to create automatically, infer automatically, this multi-cylindrical image that they can be used in real time for creating a synthetic view for the immersive exploration. And then, of course, now this year there seems to be an explosion of the neural radiance fields. The neural radiance fields were explored also for the exploration of indoor panoramic scenes. And here at this CVPR, you will see a method is called HEG-on-F that is extending the concept of neural radiance field to spherical grids with conversion to spherical coordinates. The input is a casual 360 video made with a fast rotating operation, and the output is a free viewpoint rendering of the system. So I would recommend you, if you are interested, to go to the poster session where the HEG-on-F is presented. And finally, it's like, there is work in progress from our team that is related to creation of this view synthesis by adapting generative adversarial network solution. So in general, the motivation for our work is that the state-of-the-art solution need a complicated setup for the acquisition of videos or with coherent information. And most solutions also, they have problems that they need complex training and complex inference, and they rely on explicit or implicit geometric estimation. And there is need, especially in the real reality applications, to have an extraction that is low latency for novel poses in a way that you can have a real-time extraction of perspective images, and they can respond to the 6 degrees of freedoms, both translation and rotation. So that was the motivation for our activity. And here I will present only the key ideas of our solution. That is, like we propose a client-server architecture in which we have a thin WebGL client that is managing the head motion and is connected to the extended reality setup. And on the other side, there is a server that is managing inference and computing image for the head translation. So in this way, we are able to obtain real-time performance like 70 Hertz refresh and 10 frames per second panorama updates for a workspace that is around 30 centimeters. And the solution proposed also is respecting Atlanta Award model constraints, like most solutions that we proposed during this tutorial, and is using gravity-aligned features and low short-term memory for the managing the spatial relationships. So it's like this is mostly one of the key ingredients of the solutions that we proposed a long time. And there is also, it's like the proposed solution is based on depth and layout position for constraining. And this is, a very short preliminary result of, how the system works and how is generating a 3D node pose in which you have the depth cues of related to the scene. You can. And this now comes I come to the second part of the talk. So this is related to the scene modification. So how to perform data-driven editing of the scenes. And in general, when we want to support this kind of modification, we want to do operations like adding, removing objects, or we want to place point of interest. We want to put multimedia links, 3D multimedia links, for example, to move different rooms. We want to add annotation. These are standard solutions, you know, it's like that can be managed easily in most softwares that you can find online. And also that is much more interesting than, yeah, at least for our community, we would like to have solutions that automatically perform appearance modification. Like, for example, we would like to change the lighting condition of the indoor panoramic scene. And yesterday there was at the civil workshop and a very interesting talk from one of the guys at Zillow, and they presented the results of a paper that they published at SIGGRAPH last year, in which they could extract from single image the lighting information in a way, and the lighting information that they could decompose the lighting in diffuse and specular components in a way that they could completely change the lighting of the scene, and they could start and they could have ways to perform virtual staging applications, so to perform insertion objects with correct and with photorealistic lighting and shading effects. And they could also change the lighting conditions, like, for example, the direction of light coming from outside in a way to model what is the sunlight entering the room and so on. So it's very interesting paper. I recommend you to have a look about on that if you are interested to this topic. And also another desiderata for this kind of application. People would like also change the material and the appearance of the surfaces in the scene. So in general, all these kind of applications, they make, you know, they make up what is called the virtual staging, a field that is emerging nowadays. And for what concerns this topic, it's like one of the contributions we published very recently is related to diminished reality. So it's like we proposed a model that is extracting from indoor panoramic RGB image, one single image, that why is not starting? Extracting the scene without furnitures, without clutter, and with the depth signal associated to that. So in this case, you have a scene that you can use for compelling and immersive extended reality application. So you can perform refurnishing, or you can planning interior space. So here is like one simple one example of one of the results that we got with our system. It's like you have a panel exploration with the panorama with clutter, and on the right side you have the same scene completely without furnitures. And the solution is based on a lightweight end-to-end framework. So we have a solution that is able to create architecturally plausible depth of the same scene without any clutter at very low latency. And what we learn our model on synthetic data set, but we can apply also to real world cases. So you can see a few examples in this slide. And the key ideas of the method are that's like that. The key ideas is like that we have visual and geometric constraints that can be applied only at the training time, in a way that to have the inference lightweight as fast as possible. And then we provide and we propose loss functions that combine either the photorealistic coherence, and also they provide geometric priors, like Gianni mentioned in the previous talk. So in general, what we use are virtual normal to recover the salient characteristic of indoor structures. And also we can enforce the flatness and smoothness as well, again, priors that are less restrictive than Manhattan world, like the Atlanta world that we saw before. And this is the model architecture of our solution that is based on a very lightweight encoder-decoder network that is predicting and estimating the clutter inside the scene. And both the RGB image and the clutter mask, they go into a more complicated encoder-decoder network with the two branches. One branch is for extracting the RGB signal of the empty room, and the other branch is for extracting the depth signal. For what concerns the clutter, this like the output of this lightweight encoder-decoder network is a binary mask representing the position and the whole clutter in the scene. And the network is trained by performing comparison between the ground truth depth of the image with clutter and the image without clutter. And then for training, we consider a loss that is a binary cross entropy. The network is very light and is used for the preprocessing part and for going into the empty scene synthesis. For the empty scene synthesis, what we use is lightweight gated convolutions in a way to simplify training. And also for the bottleneck part, we use repeated dilations in a way that we can aggregate multi-scale contextual information and we don't lose resolution. So in this case, we avoid the increasing of number of weights and we have a solution that it can be that is lighter for performing inference in real time. And then for what concerns the losses, we have losses that incorporates both the visual terms, so it's related to the coherence of the RGB signal, and also terms that enforce the coherence of the 3D structure and of the room. So and the geometry terms are based or related to the geometric content, so the depth signal, but also we have losses that consider the latent space for performing the comparison between the ground truth and the generated image. And here we have some results. Okay. And here are some results of the output of our model. And you can see that you can see with this like interactive exploration of the scene with clutter or the scene and the scene without clutter on various scenes that are extracted from the structured 3D dataset. I can probably, and then here use a tracked exploration. And now I can probably go to the last, small part of this presentation that is a working process. And it's like related to how to edit indoor panoramas. And we just like developing a GAN-based photorealistic style transfer that is able to transfer the style from one panoramic scene to another panoramic scene. So this would provide a very useful tool for interior designers that, there's like only with one click, they would be able to apply and just like to make the one desired scene look like another scene. And we motivated our work from the fact that the current style transfer methods, they are not adequate for indoor panoramic scenes because they are not able to lack content preservation. They are mostly designed to work on a perspective image. And in some cases, like for example, the style mesh method, they need multiple poses. And they are mostly designed for applying a artistic style transfer, not photorealistic style transfer that is much more complicated to do. And the problem for the current methods are related to the specific complexity of indoor equirectangular images. That, for example, one of them is the high resolution requirements, especially for virtual reality applications. And also one of the problems is that the indoor panoramic scenes, they have a complex illumination patterns that are considered very annoying for style transfer. And finally, it's like the current style transfer method, they don't consider the preservation of geometric characteristics of indoor scenes. And also the problem of geometric distortion that is inherent in equirectangular images. So there's work in progress considers the creation of a GAN-based style transfer architecture, in which we have two key contributions. One contribution is decompose the signal of the image, the RGB image, into a reflectance component and a shading component in a way to avoid the problems related to the lighting of the scenes. And another key contribution is to enforce geometric constraints during the discriminator phase of the GAN architecture. So this, like, stay tuned, is something that it's like in the future will. And finally, there's a very few preliminary results of our current work in progress. And as a recap, so it's like for this part of the tutorial, it's like I introduced high-based technology for performing immersive exploration of scenes obtained through spherical imaging, and also for performing automatic modification of indoor environments. The limitations of these solutions are, again, that they are very data-hungry methods, so rely on high-quality, time-consuming data acquisition, campaigns, processing, annotation, and so on. Currently, we still rely mostly on synthetic data sets because they provide a lot of high-quality annotation and high-quality signals like structured 3D. And one of the issues, of course, especially that is very, very important whenever it comes to extended reality and immersive applications, is the resolution of the image and the resolution of inference that currently for most methods is still at 1024 by 512, and that you can alleviate a little bit by using modern methods for performing a super resolution like SRGAN or LAUNET. And then finally is like as a very some take-home message. So, you probably realize how the field is evolving very fast, and especially thanks to academic efforts. There are still many challenges to address, and especially to the generalization to real-world scenario and how to increase the resolution of the outcomes and so on. And actually, it's like we know that tech companies are investing huge resources and a lot of money in the field. And since it's like just yesterday, there was a presentation of the new project from Meta. It's like the project area, and Apple announced the new spatial computer they called the Vision Pro. And my student, it's like 2 days ago, pointed me out about Home GPT application that is currently that was announced online a few days ago, in which you put a picture and you have you have various version of the room with different kind of furnitures according to the style that you wanted to have. So it's applying diffusion models and so on. And of course, and that's all from my side. It's like I want to just provide a few information about my institution. That's very recent, and I don't know probably if you heard that. It's like I come from Ahmad bin Khalifa University. That's part of Qatar Foundation. It's a very young university, but very active in many research projects. And I just founded together with other colleagues a lab that is called the IDEA Lab. And we are working on topics related to indoor modeling, but also we are trying to apply machine learning to biomedical applications like histopathology or neuroscience. And of course, our background is in scientific visualization. So we are trying also to create a visual analytics solution that can integrate machine learning for different kind of domains. So we are looking for postdocs and PhD students. If you, in case you are interested to have an experience in Middle East, you can contact me anytime. And finally, again, it's like since most of the work presented here by myself is funded by QNRF, I will acknowledge again the project that is more or less paying my trip here, and the project is called A2. And that's all from my side. So I will give the floor again to Enrico for the recap and the closing of this tutorial. Thanks again for the attention. And Enrico, the floor is yours. Stop sharing.
Okay, thank you, Marco. I'll try to be as fast as possible to end the day. Okay, slideshow. Okay. I'm starting to share my screen. Do you see my slides now? Okay, let's complete the presentation. So we have seen several presentations connected together, hopefully in some sensible manner. The focus was on panoramic imaging for indoors. I hope that you learned why panoramic images are important. It's not just a random selection. I don't want to enter into details here because it was discussed, but there are many reasons that make them popular and useful. These are connected to the devices, to the acquisition methods, and to the fact that the data that you have global context, which is useful both at the level of reconstruction to extract information and at the level of presentation, because they are immersive and they allow you to feel inside the room, move your interest point just by rotating the head and so on. So it's really a medium that is interesting. We've also seen that specificity of the focus on indoor is also important. You cannot just apply regular techniques. And besides the fact that there are some application-specific reasons, reconstruction of indoors has a peculiar characteristic. First, the structure, which leads to the fact that we need to extract it because it's useful to have as information, for example, for architecture, engineering, construction, building information models, and so on. But also we have seen that it's also important to exploit it for the reconstruction itself. The second thing is that we have seen that there are a lot of challenges in interpretation due to the abundance of noise and outliers, misalignment, reflection, uneven sampling, and all that stuff that makes the problem complex and solvable only if we restrict the domain of application. Restricting the domain of application is done by imposing some architectural priors on top of the usual priors that are used for reconstruction. These priors generate constraints on the output models, but also simplify the way you can reason about the models themselves. This makes it important, as we have seen, to mix techniques that try to extract the priors from large amounts of data, in particular using deep learning solutions that use huge data sets to find hidden relation and exploit them for reconstruction, but also to use some geometry reasoning still, both to design the networks, as especially Gianni has demonstrated several times through the exploitation of gravity alignment, the fact that walls are vertical, and so on, but also to generate a solution that mix networks with some sort of reasoning to assemble the results into a coherent model. In the tutorial, we have subdivided the works and in the areas of room modeling, integrated model computation, and visual representation, generation, and exploration. I don't want to summarize everything. It was just a few minutes or a few hours ago, but we have tried to present the techniques that now form the state of the art, focusing on our techniques, but also on the very related techniques and the peaks that we see right now. And I refer to the conclusion of each of the individual talks for an in-depth analysis and the conclusion. A take-home message in general is that the field is progressing very rapidly. You have seen many works that are cited that are from last year, from this year, from this conference itself. And this means that research is really thriving. We encourage you to start from the information you received here to look up the papers and look up the follow-ups that are likely to come out very soon on all these problems. One thing that it's important to see is that there has been very substantial progress, probably in the last 3 or 4 years, in the capability of handling complex problems and non-trivial environments. On the other hand, we can also say that while this progress has been substantial, it's not really a domain where we can say we have completely solved anything. For instance, most of the solutions that you have seen work on restricted priors. Many works that you can still see use, for example, Manhattan World, which forces the application to a very reasonable but still small subset of the typical environment you can encounter. There was a question in the Q&A before about what happens for more modern rooms or for things. Yes, there are some priors that are probably better, for example, Atlanta World or similar, but still you cannot handle anything. In any case, it's still extremely challenging to reconstruct a free form architectural surfaces. There have been attempts on doing some things, for example, application to curved walls or application to particular types of ceilings and so on, but the general things you can reconstruct them, but only very approximate. One example that we have shown is, for example, a deep 3D layout with a mesh, but it's still a single connected mesh. More and more solution, as we have seen, try to relax the constraints that are imposed by architectural prior by relying more and more on a large set of examples and trying to reduce the part that is dedicated to the priors with the geometric analysis and enlarge as much as possible the part that is dedicated to deep learning and understanding scenes from examples. However, large set of examples for which grand truths are available are still very rare. In this context, synthetic data is more and more important, as it is often the only path towards generating the many examples that we need with fully labeled and error-free data. What, for example, Gianni mentioned before is that when you talk about layout, data coming from real-world scenes is limited, possibly also in types of scenes, but it's also limited in the fact that most of the annotation are done manually and sometimes are not very precise. So the emergence of large data sets with synthetic data where you can generate data with labels that you can trust is very important. However, training only on synthetic data and then moving to real-world data is still challenging. In the many papers that we have cited, not all of them, for example, apply transfer learning. It's more and more try to train on one data set and apply on another one, but results are not always very satisfying. So this work on the generation of data is probably as much important as the work on generation of techniques. One other important thing to note that also was mentioned by Marco related to the visual part is that most of the available data sets provide panoramic images still at a low resolution. The typical resolution you find in the data sets is 1K times half K pixels per image, which is okay for application like layout reconstruction, no big problem for that. They fall short for other applications, for example, precise depth estimation, or even more important in visualization on head-mounted display that right now have per eye much larger needs. So scaling the data sets is important, but it's also important to scale the solutions. So to try to apply the methods that we have seen to have them work on data which is much larger. For some of them, it's just a matter of implementation. For others, it's more a matter of rethinking the methods, especially on those that require some sort of real-time output. For example, when you want to generate on-the-fly data that are feeding some visual display. I want to conclude here. We can have a Q&A after that if you want to have more considerations on the state of the art. But before closing the presentation, I mention again the supporting material. We promised that in the next few days or weeks, we will update the tutorial website with updated information. We will put them their slides, a bibliography, and I would say also a link to available data sets. I also mentioned our previous works on that were published on the state of the art on automatic 3D reconstruction. It's still a good introduction to the problem, and you can find also information on our previous SIGGRAPH courses. With this, we are a bit late according to the schedules, but we can still have some questions. So I leave the floor to Marco right now, who will moderate the Q&A session directly from Vancouver.
Thank you very much, Enrico. We have 7 minutes for questions and for the discussion, mostly related to the second part of the tutorial, because we already have the questions for the first part. So I ask the audience if they have questions for the speakers, or yeah, if you can.
Yeah, thank you so much for the great tutorial. So are there any good 3D editor floor plan tools available, like as an open source? You know anything?
I mean, I can probably start answering. Yesterday, I saw a presentation of Zoo that is working for an important real estate company, and is trying to integrate many data-related data-driven solutions. Later, I can probably provide you details about this solution for free. For free online resources, floor plan, I'm not aware about that. Actually, this topic is a very big interest for many companies, and whenever they have some solutions, they try to make it, well, like example, Matterport is, is a sort of integrated solution that is commercial for doing this kind of operations, editing on different kind, also not only on panoramic images, but most solutions, also commercial solutions, they try to fuse a different kind of information acquired with different devices, not only panoramic images. That's it.
Thank you.
I don't know if Gianni or Enrico want to add something. Gianni, you have
Yeah, I have another question. Thank you, Giovanni and Enrico and Marco. So what I saw in your presentation, there are two methodologies to get the floor plan. One is, structure from motion, like the grammetry that you can create a point cloud and the sequence of the 2D images. And from that, you can do the floor plan. The other approach is building a panoramic, such as the Matterport, and getting that as a floor plan output. So having said that, we see NERF is coming, up, and we can provide a very realistic virtual tour and experiences with, like, say, video photogrammetry input. So is there a room for 360 imagery in that situation? Consider that the input is going to be just an iPhone or Android phone, not 360 imagery.
I would, it's like actually I attended the presentation from last presentation for Furukawa, and they are going on toward that direction. So you touched a very good point, and I'm expecting something will come out really soon about application of NERF for different kind of operations, even for registration, even for integration of multi-floor image. That's like as expectable, and for in the next future. Then I don't know if Enrico and Gianni can add something about that.
No, I don't know. You want to start then?
No.
Okay. No, I want just to start that to say that as you have seen during the tutorial, the boundary between the different techniques is sometimes blurred in the sense that it's not that every method using the same pipeline and so on. I see, for example, here several lines where we could classify the applications that we have. The first thing is what you can do with from a single image. NERF, most of the time, there are some variations, but NERF most of the time requires multi-view input to generate the models. Several of the solutions that we have presented are more like what you can extract from a single view. Okay, so what you saw mostly before the break and so on. The other thing is the density of the input that you require and so on. And also the fact that it's possible to do NERF also with a panoramic imaging as input and mix the two solutions. So I think that there can be some convergence in all these methods, but also that depending on your application and on the constraints that you have, both on the capture side, but also on the display side, you would want to choose one solution or another. For example, rendering an NERF is still more costly than rendering a geometric model if you can extract it, and so on. Okay, so I mean, it's a very good period to try things and see if they work, if you want to mix them, but also you can have to choose exactly the type of techniques, also depending on the constraints.
I have last question. So do you know an open source for creating 360 imagery with, let's say, smartphone like panoramic imagery?
Yeah, stitching, open source stitching solution.
Yeah, open source stitching solution.
Actually, it's something that was available, quite a long time ago, like 10 years ago. But recently, I have no. I don't have an idea. We should. From my side, I don't have an answer for this question. I don't know if Enrico Gianni has open source solution for stitching.
To create.
No, for creating panorama, of course, there are all the stuff related with the replica, habitat, and a lot of stuff from Meta and Facebook research. I mean that have,
open source.
Yeah, it's open. It's open because they have the data that come from Matterport sensors, and also they provide open source tools in order to render panoramic from a different point of view with respect to the instrument actual position. Okay, so you can render many panoramics, okay, even interconnected from your custom positions, okay, from there. The counterback of it is that they are not real images, they are just rendered. So sometimes you have a more dense geometry in some part of the building, and there you have a photorealistic appearance. In other parts, also if you look to, I don't remember now the papers, but many papers have mentioned the use of the replica and habitat and Gibson to render, but it's not possible to use for the wall floor plane because in many parts there are always missing parts, okay, because they miss the real samples, so the data is not very complete. Such kind of data is useful if you want just to build something of large scale, like multi-floor and so on, okay? And or even if you don't need a very accurate details, I mean, okay, and not photorealistic, but anyway, they are very useful. They are also expanding such kind of data set. Okay, so you have to search on the internet about such data sets. Okay.
Thank you. I think, oh, yeah,
Okay, so I have a question for Marco.
yeah,
So for the demo you showed where you can remove the clutter, so the input is the panoramic image.
Yeah.
So did you do everything in real time? Like you take a picture and it's panoramic image and then the removal and the rendering happens at real time, or it's the process offline?
I mean, it's like the video that you showed is offline, but actually the inference is in real time. I think we have times for the instant removing. It's like we can stay at around 10 frames per second for the inference. For the inference, it's like extracting. You have a. Let's suppose that we have your camera, spherical camera around, and it's like the inference for the.
Oh, so the what device are you using? Is it a mobile phone or?
No. It's just generally, it's like it's like we didn't integrate in a mobile phone.
Oh,
It's like the inference is still, the timings that we report are for the desktop inference.
Yeah, because if I
Not
can-
integrated in a device yet. That's a point.
if I can say something about the emptying room, okay, as Marco said, this is very fast. Okay, so theoretically, you can reach interactive rates, but the point is that the solution we proposed in that work is focused on static single images. So I think it's fast. If you try to apply that to a video, for example, a panoramic video, it's work, but there is not consistency between frames. So it's the same problem I have mentioned at the end of the first talk I've given. So coherence between single image inference, okay, is still challenging for many reasons. Okay.
okay, sure. Thank you.
You're welcome. Bye.
One last question.
Okay.
So are there any open source virtual staging software? So how did you do the virtual staging?
No, this software, it's like prototype developed in-house.
So is there anything, let's say, open source that you build on top of it, or?
Not yet. What we plan to do. Yeah, we plan to release.
Is there anything in the literature?
And then for virtual staging solutions, you should check the paper that I mentioned about the Zillow related to interactive lighting.
Okay.
Probably they released some. There is the code for that. Will be,
Thank you.
You're welcome. I think that's all. It's like now only 2 persons stayed because the people is angry. Thanks again for the active participation in the tutorial. I hope you get a grasp of what are the problems and what are the current solutions in the field. A lot of stuff will come in the future, we expect, because the field is is very interesting and with a lot of commercial and applications and so on. Thanks again, and
Thank you. Thank you, everybody.
Thank you. Bye.
Wait, I give you also my.
Yeah, thank you.
And thanks again for all the questions. Really.
I think this is.
What we get score? No, there's not. No, wait. I give another one. This was yeah.
Thank you.
Yeah, this one is. Thanks
Thank you,
again. Contact us if you have additional questions and additional curiosities.
So, in fact, what I build is a mobile app for floor plan creation. So it's funded by the National Science Foundation, NSF. Yeah, it's like called Opal AI Scan to 3D. So it's on LiDAR enabled phones, but we use structure from motion to.
Not yet data-driven solution.
So what do you mean by?
It's like a deep learning.
Yeah,
Yeah,
deep learning.
yeah.
end-to-end deep learning. So I'm
Ah.
also a machine learning scientist at NASA's JPL.
Okay,
So that's how the things got. Yeah.
cool.
Okay. Thanks.
Good luck for, for next,
Yeah. Yeah. I wanted to chat with you maybe after.
yeah, sure. It's like, let me say hello to the guys, unfortunately they are not here. Okay, we can close the communication here. We can leave because they are still recording, I think. Yeah.
Yes,
Okay.
we can stop now.
Again,
Okay.
we stop. I think it's lunchtime there and dinner time
Okay,
here.
have a nice lunch and
Bye-bye.
dinner.
Bye.
Bye-bye.
Thank you.
Bye bye.